Above-ground tank designs have advanced dramatically since the leaking underground tank rules came into effect in 1988. Many people like the basic visual assurance that is missing from an underground system, but like anything, they have their design challenges.
Above-ground fuel tanks are made of steel because of its inherent fire resistance compared to fiberglass or plastic tanks. They are more flexible than underground tanks and can therefore conform to a variety of site requirements. The tanks need to have secondary containment, and if this is provided by a concrete dike or room construction, then a single wall tank may be suitable. Double wall tanks are also common for several reasons. A. They exclude rainwater for tanks located outside. B. The containment area is closed and testable. And C. The steel containment wall is impervious to fuel absorption, which can be a problem with untreated concrete. Fire-rated tanks utilize an insulating material between the primary and secondary walls to provide a 2-hour fire-rated protection for the tank contents. For these reasons, the fire marshal may require that above-ground tanks be fire-rated. Tanks in buildings may also have a requirement for fire rating. However, this protection is typically provided by the fire protective room construction. Tanks are typically horizontal tanks with integral steel supports and openings at the top. Vertical tanks are sometimes used where space is not available for horizontal tanks. Where vertical tanks are used, consideration needs to be given to servicing equipment mounted on the top of the tank and specifications for level transmitters and other equipment that will require a length beyond their normal range. Cylindrical tanks are less expensive than rectangular tanks because they are self-supporting without internal bracing. Rectangular tanks have a more efficient footprint for a given capacity and can be built to specific outside dimensions where required for placement inside buildings. Vent terminations allow the tank to stay at atmospheric pressure as the fuel level changes. Their primary purpose is to disperse vapors, exclude water, and prevent insect or bird intrusion. Emergency vents are sized to allow excess pressure to dissipate and are designed for vapor generation that would occur under fire conditions. They are provided for both the primary and secondary tank space. While underground tanks can receive fuel by gravity, above-ground tanks require pumped fuel delivery, typically via the fuel delivery truck pump. Tank fill hardware attracts a lot of attention because of the opportunity for spills and overfills during fill operations. Spill containers of 5 to 15 gallon capacity surround the fill pipe to catch any spilled fuel during disconnection of fuel delivery hoses. The fill pipe adapter and lockable cap allow for a tight hose connection to the tank to prevent leaks. The fill pipe drop tube directs fuel delivery to the bottom of the tank to minimize vapor generation within the tank. The overfill prevention valve is installed within the fill pipe drop tube to stop fuel inflow at the tank at a level below 90%. The valve is a fully mechanical device that operates with a float rising to close the valve. While overfill valves for underground tanks typically resist only a gravity feed pressure, valves for above-ground tanks need to resist delivery pressures of 100 psi. Most suction systems with remote above-ground pumps utilize foot valves. The foot valve is a check valve designed to be installed vertically at the bottom of the suction pipe within the tank. It maintains the suction line full of fuel to assure pump prime. Extraction fittings are often used at the top of the tank connection for the suction pipe to allow removal of the suction pipe and foot valve for inspection and servicing. Above-ground tanks typically have a mechanical type level gauge for direct reading of tank levels as a backup to electronic gauging systems. Above-ground tanks are commonly located such that fluid level in the tank is above the point of use. Therefore, inadvertent fuel could be siphoned from that tank. To prevent siphon flow, an anti-siphon valve is typically located at the top of the tank. The valves are either fully mechanical or an electric-operated solenoid valve can be used. The fully mechanical valves are usually configured as a normally closed valve with an adjustable spring resistance to equal the siphon head. Then a positive suction from the transfer pump allows the valve to open and flow. Electronic level gauging equipment consists of an electronic transmitter, typically a float traveling on a stem based on a mag principle for accuracy. In addition, the tank should have access for manual gauging using a wood measurement stick. Continuous electronic leak detection is provided for above-ground tanks, sumps, and piping. An above-ground tank at grade, adjacent to a building, will look as good as a tank can look. For that reason, they are typically enclosed by architectural walls or fences. The tank needs to be located so that a fuel delivery truck can drive adjacent to it for filling, although remote fill stations can be used if this is a problem. The tank's and fuel delivery area is designed to be separated from the storm drain inlets. This is to allow any leaks or spills to be cleaned up before flow to stormwater systems. While double-wall tanks provide protection for the tank contents, the tank equipment and piping connections are a source of fuel leaks that can be difficult to double contain. In some climates, a curbed area around the tank serves this purpose, or otherwise equipment can be mounted in a containment enclosure on the top of the tank. Above-ground tanks are sometimes used along with underground piping systems. The transition from underground to above-ground piping at the tank is commonly performed at a transition sump where the double wall systems may terminate and differing pipe materials can be joined. Design coordination issues include civil, geotechnical, structural, and electrical issues. Here is a list of some of the most common issues. Architectural enclosures for tank area, location of drainage structures, location of underground conduit for power and control.